Okay, so I'm going to stay up here and continue with our first kind of content segment. And this is the principles of HPC I/O. So this is the most high-level talk you will hear today. And the goal here is to kind of give you some concepts that we'll kind of refer back to as the day goes on, so you know why we're doing some of the optimizations and things that we're doing. And I'll start with the definition first. When we say HPC I/O, what do we mean? So this is just storing and retrieving scientific data on a high-performance computer. So that's simple, right? Almost always, not quite always, but almost always, this means using a parallel file system. And parallel file systems can store and retrieve enormous amounts of data very quickly. It's great. This is a hard job. We'll find out why in a few slides here, but it has to orchestrate interfacing with your application, interfacing with system software, organizing a bunch of storage resources. And if the parallel file system doesn't do its job well, or if maybe you use it suboptimally, that's a problem, because the time you spend waiting on your data is time that you're not calculating, right? And so you're wasting your CPU time allocation if you don't access your data effectively. So almost the whole day, we're going to be talking about how to use a parallel file system well, how to properly feed and care for it so that you get everything you can out of your file system. So let's see what a parallel file system looks like on the scale of machine that we're using in ATPESC. We'll start with what a workstation or a laptop might look like. As you know, there'll be a handful of cores there, or maybe several cores if you have a nice workstation. There's a storage controller and one or maybe a few hard drives. And so if you want to access a byte of data, it doesn't take long to get from your compute core to your storage device. It just goes through a controller, hits the device, and comes back. So the nice thing about that is that the latency is really, really low. It doesn't take long to get a byte from one place to the other. The bad news in that setup is that the bandwidth is not great because you can't go any faster than that one hard drive or that one SSD in your laptop. And so your rate of how quickly you can move data overall isn't very high. If you compare that with what a big parallel file system looks like, and this is pretty typical conceptually for any of the parallel file systems at a DOE facility. Of course, they don't have one or two hard drives. They have hundreds, thousands, probably tens of thousands of hard drives. They're disconnected from the compute resources, so they can be managed separately, they can be shared. So you may have thousands and thousands or even millions of cores, and they can reach any of tens of thousands of hard drives. And it turns out it takes a lot of hardware to make that happen. If you want to access a byte of data from your application, it goes from your compute core, probably transits the network fabric that you use for MPI also, goes through bridge nodes that are connected to a network switch, bounces through a couple network switches, finds a file server relays it to a RAID controller that does kind of redundancy and striping and stuff, and then goes to a big pool of storage disks. And that takes a while, relatively speaking. This all fast hardware in the path, but it's a long path. And so the bad news is if you want one byte, it's going to take a little while. Slower than your laptop, in fact, to get that byte, even though this is an elaborate, very expensive storage system. So the latency is actually very bad. I want you to understand that the time it takes to get one little piece of information is not great. What you get in exchange, though, is incredible bandwidth because you can activate thousands of hard drives simultaneously to pull data out. So if you're moving a lot of data and you can get all those running at the same time, you're in good shape. If you're in a situation where you're waiting one at a time for one piece of data, you're in a bad situation because that's the worst case is you're latency bound. So we're trying to optimize for the good properties, which is the incredible bandwidth, and de-emphasize the bad properties, which is the latency in these systems. The other thing I want to get across is, and I mentioned it already just now, is striping. So there's many hard drives. Usually your data set, if things go well, is not stored on a single hard drive. It's divided up across a large number of hard drives to take advantage of the parallelism. And so it may use multiple servers. Each server may use multiple hard drives up under it. The way we split up a file and divide it up among those devices is usually called striping. So you'll hear us talk about striping through the day. And different file systems on different computers have different policies. They might do kind of like a round robin, like a megabyte, and then wrap around. It might be kind of random. They may kind of scatter things in the storage system, and sometimes you can tune it. And that's a big performance optimization if you can kind of stripe your data in a way that makes sense. And that's something that will kind of factor into how we get performance out of these systems is how the striping works and when it's working for you and against you. And so that's at a high level what it is, but the other thing you should be aware of is that there's some wrinkles. Every HPC system at this scale is unique. None of them are identical. They're built for the specifications of the facility, the kind of applications they expect to run, and so they tend to have different features, not only in the compute side, but also in the storage side to match, what they're trying to accomplish. And so you may have different things you'll hear about depending on what facility and what compute system you're using. Some of them have in-system storage, so Summit would be one example. So there's hard drives that are attached to the compute nodes that you can use for some things. So that gives you a path that gives you the low latency that you would expect from a workstation, but it's not shared like a big disaggregated storage system is. Some systems like Cori at NERSC have burst buffers. A burst buffer is another layer that is very high performance but not very big. So you're kind of doing a trade-off between kind of the cost of more advanced and closer storage hardware versus the capacity of your big file system. And everywhere, whether it's at Argonne or Berkeley or Oak Ridge or anywhere else, tends to have multiple file systems because they found that number one configuration doesn't suit all purposes, and number two, sometimes file systems go down, right? They break sometimes, and they want to have other fallback options. So you may have a file system that's for your home directory, one for Scratch, one for projects, one for sharing things, and it's important to kind of look at your facility documentation and make sure you're using the right one. So I'm going to pause here for a minute. This is a lot of conceptual information, and I'm kind of revealing a lot of complexity in these file systems, but the goal is not to scare you. The reason I'm showing you this is to make you understand that these storage systems are special and take special considerations. And the tools and techniques that we're going to show you today, sometimes they seem kind of complicated, or why can't I just open the file and do what I want? I mean, this is why. There's these tools are helping you tame some of this complexity and helping your code do the right thing, even at scale. And so this is kind of some background for why we're going to teach you the things that we teach you today. So if we look at that's what the storage systems look like. Now, how does your application access it? An important thing to know is that a parallel file system can look just like any other file system. You can open and close files, read and write them. If you're using standard I/O text operations, you can fopen and fprint to them, that sort of thing. If you're using Fortran or Python, you have bindings that are just wrappers for these things, essentially. And all the data is in directories and files. And we refer to this as the POSIX interface. This is the basic kind of storage interface that any computer has, really. And the great thing about POSIX is it works. I mean, it's been around forever. It's great for compatibility. So if you write code, from 30 years ago on some Sun workstation, it's going to run today on an HPC system using POSIX. That's great. The bad news is this API was designed way before anyone thought about large-scale parallel computing or parallel file systems, and the API doesn't match. It's kind of an odd fit for what we want to do sometimes. And there's some quick code there, what it looks like to open and write and close a file. But if you look at the arguments to open and write and close, there's no concept of parallelism. There's no way to say, I'm the third process out of 1,000. Everyone is independent, and there's kind of shaky semantics for what happens when people access a file concurrently, because they weren't thinking about that when they designed this API. The file descriptors are stateful, so if you have 1 million processes open a file, there's 1 million file descriptors that all have a little bit of information about the file. That's not great for scalability or kind of coherency. The file position is implied, so when I write, it's assumed that it's going to be at the beginning of the file, and if I write again, it will be a little bit further into the file. It's like a stream. Streams aren't great if you have 1,000 people trying to use the same stream at once. And the files are unstructured, it's just bytes. There's nothing telling you what each byte means or what is the significance of different parts of the file. So if you're trying to use this for a parallel application, I'll give you some examples of how this can kind of go sideways for you, so you're aware of, you know, some of the dangers here in a parallel file system. So I'm going to go through a few examples. They're not real complicated. The first one is, imagine you have two ranks in a parallel application that both want to write to the same file. And let's assume, for simplicity, that they're writing to entirely different parts of the file. So one's at the beginning of the file, one is 32 megabytes into the file. And they're going to write a reasonably sized chunk into it. So the nice thing is, you know, if your file is striped the way you want it to be, it probably will go to different servers. So you'll activate two hard drives at the same time, and you'll get some parallelism there. And there's no contention on the actual write, because it's going to different servers and to different file systems, and they can each do their own thing and get it right. A couple of things, though. One is that, again, these operations are independent as far as the file system knows. You did an open, write, and close on one process and an open, write, and close on the other. It doesn't know they're related. So the storage system can't do anything to organize that traffic as it passes through the network. They're each going to pick their own way. They'll maybe conflict, maybe they won't, maybe there'll be contention. It may not be organized ideally. It'll probably be okay though. The second thing is, it's not realistic if you're doing a simulation that everyone's going to be spread out all over the file, right? At some point you're going to be adjacent to each other in the file, working on a dense data set as you kind of partition up your grid that you're working on. So what does that look like if you're writing to adjacent parts of the file? This is the same example, but let's assume that we're writing 256 kilobytes in one process and 256 kilobytes right next to it in another process. What happens when you do that? They still don't conflict, at least at a logical level. They don't logically conflict. But what will happen is, you might imagine, they're probably going to go to the same server. They're probably going to go to the same hard drive even, because the striping is not at the granularity you picked. It's not split up in 256 kilobyte increments. It's split up how the file system wanted to do it, probably much larger. But they're still not conflicting. They're going to the same place, but they're writing different bytes. But what will happen under the covers is this will be a conflict. The problem is that because the granularity is bigger, let's say the file system is operating in units of a megabyte or 4 megabytes, there's probably going to be false sharing. So one process will get control of that block and write its data. The other process comes in and wants to write it, and it will be blocked and serialized. So only one will happen at a time, then the next one will happen. And it may be worse than that. One of them may cache the data all the way up to a compute node. The other one comes in and conflicts. It's got to release the cache, release the block. The other one comes in, it caches. So you can get some thrashing, because these things that seemingly aren't conflicting with each other actually are under the covers. And so a lot of what we're doing today is kind of trying to avoid situations like this. And they're hard to do by hand, but they're easy to avoid if you use some of the tools that we teach you today. You might also look at this and say, well, the only reason I'm having this contention is because they're all writing to the same file. What if I just use different files? That is something you can do. I'll walk through what happens when you do that, so we can understand some of the possible pitfalls here. But same example. This time, one rank opens file A and one rank opens file B instead of trying to use the same file. And they both write at the beginning of their own file. So the writes go to different places. They go to different blocks. They're unrelated. There's no contention. That's great. The problem, though, is if you remember, we're using the POSIX interface, and you have a hierarchical set of files and directories. So when you do open, there is a conflict because they're in the same directory, and the file system has to protect to make sure you don't have two files with the same name, or some permissions conflict or something. So you've moved the point of contention so that it's no longer in the write path, but you still have one at the open time probably. There's two other problems. One is that you're hurting your ratio of how much effective work you're doing for how many I/O calls you're making. So instead of moving 256 bytes of data with one call, you now got an open and maybe a seek and a close and so forth. And that means that the file system has to update the file name, has to make sure the permissions are right, has to update the file size, do that separately for everyone. So you're getting more, we call that metadata, this extra information about a file. You're getting more metadata overhead for the unit of work that you're trying to accomplish. And at small scale, that's fine. You won't notice it. As you try and get your application to run bigger and bigger and bigger, it will become a problem one day. That's a large scale problem, not a small scale problem. And finally, now understand if you have a science use case that has many files, that's one thing. But if you're trying to make many files just to make your I/O faster, you're putting the work on yourself, because you're going to end up with a million files when you just had one before. And now you've got to copy a million files. You've got to figure out how to analyze a million files. It's not a great situation. So we're going to try and learn some strategies for how to make one file go fast so that you can kind of simplify your workflow when you can. So the theme that connects all three of those kind of problem cases that I showed is that, again, the POSIX API doesn't provide enough information to the file system. Every single application is independent. There's no connection between them. And so the storage system can't make any decisions about how to organize what you're trying to do. Even if you know that you've got 1,000 processes, they're each taking a chunk of the same file, the storage system doesn't know that. It sees a bunch of conflicting requests and tries to sort them out as best it can. So we're going to try and get away from that. And help is on the way. That's what we're going to spend the bulk of the day talking about, is how to do just that. We'll often be talking about high-level I/O libraries. These are things layered on top of the file system that give you different interfaces. And they're portable. They run on a lot of different machines, and they'll change what optimization strategies they do depending on the machine you're on. Of course, I'm sure there's people in here that are using POSIX and have a good reason to do so. Don't worry, we'll help you too. We've got some good strategies you can use even if you're in that scenario. And a big part of today is also how to just measure and understand what your application is doing. So regardless of what strategy you're doing, how can you tell if it's good or bad or how it could be better? And I'll go on a little digression here. This is kind of a pre-sales pitch for things that you'll hear later today. And our other speakers will do a better job of covering this in detail, but I want to get the concept out in front of you early. When you look at high-level I/O libraries and what they're trying to do, they're trying to bridge the gap between scientific applications and the parallel file system, basically. So if you look at what most scientific applications want to do, they have structured data, usually. So you may have a grid, a mesh, a multidimensional array, different data types, maybe an adaptive mesh, maybe scan lines, depending on your data, but there's some meaning behind the data. It's not just bytes, right? And then there'll be some description of that data, whether it's a header that says, okay, this chunk is this part of the simulation that I'm looking at, or this value. You may have attributes, say this came from this instrument, we simulated this way. There may be timestamps, that sort of thing that help you understand what's in the data. If you look at what a parallel file system can give you, again, it's just subdirectories and files and bytes. It doesn't understand any of those things. There's a mismatch there. And of course, the performance can be quirky, which I just spent some time walking through why it can be quirky. So you can bridge this gap yourself. You can make up your file format, and you can say, for example, I've got a frequency attribute. It is an 8-byte floating point number, and it is at offset 4096, and that's how I'm going to remember it. The problem is then you're putting the burden on yourself to remember where that is and document it. If someone else takes your file and wants to do something with it, how do they know it's at that spot? You've got to take ownership of that. And it may be that one day you'll find a machine where, boy, it would really go faster if I could put this at offset 8 kilobytes, and you can't because you've hard-coded this selection in there. So the answer to this is a data library. And there's examples include HDF5, Parallel, NetCDF, and Audios. And all these things are bridging this gap, giving you an interface that looks like scientific data and organizing it in a way that makes sense for a parallel file system. And what you get for doing this is, of course, you get a more expressive interface. Instead of reading and writing bytes, you are accessing arrays and subsets of arrays and data types and so forth that make more sense for science. You get interoperability. If you write a NetCDF file I don't know, if you wrote a NetCDF file 20 years ago on a machine that doesn't exist anymore and you tried to open it today on Summit, it'll work. I mean, it's interoperable. The bytes are organized in a way that makes sense. It's well documented. Performance. In addition to the file format, these libraries all do some optimizations. They're usually platform specific, and they're adjusted for different platforms as they're deployed. And future-proofing. These data formats live on. They've seen storage technologies come and go, and they'll see storage technologies continue to come and go in the future, and they'll keep working. So we'll be talking specifically about parallel net CDF and HTF5 in particular later this afternoon. But this is why you want to think hard about using those if you're not already. And so let's say you've done all this. You've absorbed all this great information about how to tune your applications. You're using the APIs and tools that we're giving you, and you think you're doing everything right. Sometimes you can still get a performance surprise. I want to be clear about this so that you understand this when you're measuring your code and trying to apply the things you learned today. Storage performance on a big machine is going to be variable. It just is. I mean, I wish it wasn't. We fought hard to make it not be that way, but that's the way it is. There's a few reasons for this. One is that if you have 10,000 hard drives, they may have all the same specifications and have been manufactured at the same time, all that. They will never perform the same way at the same time because they do things internally. There's moving parts. Even if you have SSDs, they do garbage collection and trimming and all sorts of things. And so they do these things at different times and in different ways, and they just never run at the same speed. Some of them get hotter, whatever. I mean, they're just not, they're temperamental. The other thing is that you are sharing a file system with lots of other users on the system, lots of other applications on the system. So this is different from your compute resources. If you get an allocation, a job allocation, you have your compute cores, you have your accelerators, they are yours. Nobody else is running on those while you've got them. Storage system is absolutely not like that, generally speaking. We'll hear about some exceptions later, but you're sharing this with everybody else. If they're writing hundreds of terabytes while you're trying to write hundreds of terabytes, you can't both get all the bandwidth. Not only that, there's data transfers going on, there's archival going on, there's administrative things going on. So you just really have no idea what's going on a storage system while you're trying to accomplish your work on there. And so in a way that's totally different from your compute resources, storage resources change performance over time. So what do you do about that? Really, the only thing you can do is take multiple samples and understand what the range of performance is for your application. The thing that I want to caution you against is you're measuring your code and getting 1,000 megabytes a second and then making a change that you heard about today and you run it again and you get 1,010 megabytes a second, right? You're like, great, I got another 10 megabytes a second. You didn't. That's noise. That's just how much it changes from run to run. So be careful of that. And this is an illustration, a figure from an old system that's long since been retired, but you'll see the same thing on today's systems. We ran 15 I/O benchmarks on the same day, same exact configuration, same build, and we measured the performance. Sometimes the I/O completed in 50 seconds, sometimes it completed in 65 seconds. It was often bunched in a tighter window, but there's peaks and valleys sometimes. And so you need to understand if you make a change, are you within that range of what your application can do or not? And if you've done storage for a while, if you talk to us, we can probably give you an idea. You can say, well, I saw this and it's this now. Is this noise or am I doing something real? And we may have a feel for that based on our experience with the systems, but for yourself, you might need to do multiple runs and make sure you kind of understand what's going on. Do some micro benchmarking. I know these codes are big. You don't want to use your whole allocation trying to squeeze a little more I/O out, but find a way to limit it down to the piece you really want to look at and measure it, see what's going on. And we've got some exercises today that you can use to look at this, and it'll kind of help you get a feel for what today's machines are like in this regard. And kind of a last concept I want to leave you with for this segment is, we're going to do everything we can to help you today and teach you some strategies, and we can help you hands-on with your code. And hopefully you'll come out and you'll have some improvements, whether it's improving your performance or kind of getting some more capabilities that you didn't have before. But it's never done, really. Things change. You'll get allocations on new systems that have different properties. A student may change the code that you're operating on to add a new feature. Your science focus may change. You're looking at a different phenomenon that you weren't before, and so conditions kind of change, and you need to be ready to kind of roll with it and improve your application over time, depending on what happens. So a lot of this is learning how to observe your application, how to measure it. We'll talk a lot today about a tool called Darshan that helps you do that. So if you learn this one time, you'll always know how to measure your application and understand what it's doing. We're going to try and equip you with some background information, like the material from this talk, that helps you understand why you might be seeing what you're seeing, so you can kind of orient some context with the measurement that you see. Spoiler alert, I'll warn you right now, if you go to any of the facilities and look at the specifications for their file systems, almost all of them give you a performance number. They say this file system can do 100 million gigabytes a second. You can't get that. That's not realistic. Those numbers, I mean, technically it probably could do that, but it can do that if you configure the file system brand new out of the box and you have the whole system, nobody's touching it, nobody's breathing on it. We're going to run a benchmark, optimize it, and that's the number. That's not the real world. So don't rely on that as your context. We're going to try and give you some better context today for how to understand your measurements. You want to look at what your options are once you measure your application and you kind of have an idea whether that's good or bad. There's resources at the facility that help you tell you what tools are available, and we'll tell you about a lot of them today. And we want you to be able to implement your optimizations. So that's, this is all about strategies for how to understand what's going on, implement changes that'll make it better. So just try and take this with you as not so much one and done. I'm going to learn some things, I'm going to apply it, we're good. This is kind of an ongoing process that we want to teach you how to be able to do, so you can keep doing it for however long you need to in your application. So with that, that's the principles of HPC-IO. Actually finished a few minutes early, so if folks have any questions about anything I talked about, I'm happy to answer them if I can.
I have one question. So, why is the storage, like the POSIX API, is so much important to the storage community? Why we don't want to go and keep on the store Deus like object storage interface?
Yeah, I mean, that's more of a, it's inertia really. So there have been a lot of efforts to do other things, and the Aurora system at Argonne is going to be one of the first DOE systems that has an object store as the primary store. So we're making some headway, but it's really just been, I guess part of the problem I would say is that high performance computing isn't actually a big market in terms of industry. And so the companies that make these big storage systems don't have a lot of incentive to make something that's just for HPC. They've got to make something that works for other markets, and then we steal it and tune it and make it better for HPC for what we want to do. So it's just been hard to make headway on doing something better, really. Thank you, everyone.